Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting the lecture 3 of module 3. So, the topic of our today's lecture will be the application of Levy's method to various types of problem. So, earlier we have seen that Levy's method can be applied to a specific boundary conditions for rectangular plate. That means, two opposite edges must be simply supported and other two opposite edges may have other conditions. So, based on that we found the solution for different types of problem where the loading was distributed fully, partially and strip loading, and boundary conditions we have taken that it is simply supported on two opposite edges and other two opposite edges was fixed as well as simply supported. The simply supported on all edges condition was earlier analyzed by Navier's method, but in the last class I have shown you that this type of problem can also be solved by Levy's method, because Levy's method, although the derivation is slightly complicated, but computation becomes easier because of single summation. So, that is one advantage of Levy's method, and there is more generality in application due to relaxation of boundary condition that two opposite edges were all the edges were simply supported, which are the essential or the only requirement in case of Navier's method. Now, we shall use the Levy's method to solve the problems of plate, rectangular plate, which is simply supported along all edges, but subjected to edge moment. The edge moment problem is important to obtain the solution for other edge condition. For example, this all edges clamped. So, that type of plate can be solved by using the Levy's method, superimposing the 2-3 solutions obtained by Levy's method. So, today we will discuss this thing. Okay. So, today's outlines of the lecture is simply supported rectangular plate subjected to distributed moment along two opposite edges. Then we shall consider symmetrical and anti-symmetrical cases for the moments. Then number 3, solution for any general distribution of moment. In this second point, I mentioned that symmetrical and anti-symmetrical cases, but if there is any general type of distribution of moment, say at one edge it is say uniformly distributed moment of magnitude say 5 kilonewton meter per meter. In the other opposite edges, the moment is say 10 kilonewton meter per meter. So, in that type of situation, it is neither anti-symmetrical nor symmetrical. So, any general type of distribution also can be handled by Levy's method, and that we will discuss today. Then use of the results so far we obtained in case of the uniformly distributed load or partially distributed load, and then the edge moment will be applied to find the solution of the plate when two opposite edges are simply supported and other two opposite edges are clamped. So, that type of problem actually was solved in my earlier classes using Levy's method, imposing the boundary condition at the other two edges, because the plate was symmetrical about the x axis. So, we applied the boundary condition that y is equal to plus minus b by 2 for a rectangular plate of size a plus a cross b. Now, that results will be obtained by superimposition of edge moment conditions. So, after delivering this topic, that the problem of rectangular plate with two opposite edges simply supported and other two opposite edges clamped, then we can further proceed to find the solution of the problems of rectangular plate whose all edges are clamped, because clamped places are very common in practical application, and we require to find the solution, analytical solution if exists. So, it is shown by superimposition principle using the Levy's method, the exact solution of the clamped plate, that is clamped plate, I mean that all the 4 edges are clamped, can be obtained. Okay. So, now let us consider a plate, rectangular plate of side A, the length is A and width is B, subjected to distributed moment along the edge y is equal to 0, the moment is m1, which is distributed along the x axis in a functional form that I have written f1 x. This may be a constant also or may have any other variation. Then on the opposite edge y is equal to b, here you will see that the moment m2 is acting, and which is in the functional form is expressed as f2 x, f2 is a function of x. But since the axis is considered running through the center of the plate, so the S conditions are defined as plus b by 2 and minus b by 2. If this is the direction of positive x axis, the upward direction, then the top edge will be condition at y is equal to plus b by 2, bottom edge will be at the condition y is equal to minus b by 2. So, we consider that moment m1 is equal to f1 x and m2 is equal to f2 x. This f1 x, f2 x may be constant also. So, in that case the edge may have the uniform distribution of moment, and sometimes this we consider a variation of moment, say sinusoidal or any other type of moment acting or linearly varying moment along the edges. So, that condition can also be handled by this method. Okay. So, let us see that since there is no distributed load, so q x y equal to 0, that parameter we know. So, plate equation is reduced to the homogeneous solution of this fourth order differential equation del 4 w equal to 0, because there is no load acting on the plate. The edge moments are applied, but that is to be fulfilled by boundary conditions. So, the plate surface the free from loading. Therefore, we have written the differential equation of the plate as del 4 w equal to del 4 w equal to 0. Okay. W is of course a function of x and y. Now, since we are adopting the Levy's condition, so we will be using a single sine series as expressed by y m equal to y m into sine m pi x by a, where the capital Y is a function of y that remains unknown, and sine pi m pi x by a is the condition that is taken to satisfy the boundary condition at x is equal to 0 and x is equal to a, because x is equal to 0, x is equal to a boundary condition is simply supported. So, it satisfies the condition at x is equal to 0, x is equal to a. But other edges, the boundary condition is here we are taking simply supported, but it contains edge moment. So, sin m pi x by a will not directly satisfy the boundary condition here, because the edge moment condition have to be applied to find out the solution of the boundary value problem. Okay. After substitution of the equation 2 in equation 1, it can be readily verified that the fourth derivative of w, fourth derivative of y with respect to y will be the first term, then your second term will be your this minus 2 m square pi square by a square into second derivative of capital Y with respect to y, and the third term will be m to the power 4 a to the power 4 pi to the power 4 divided by a to the power 4 into y equal to 0. because sin pi m pi x by a will be appearing in the summation term, and taking a general term of this series, say mth term, we can write the differential equation as equation 3. So, it is reduced to a ordinary differential equation of fourth order. So, we have seen the solution of this differential equation, that is, if I assume the solution in the form E m e to the power lambda y, where E m is a constant, and after substituting this we get a characteristic equation which will be lambda to the power 4 minus 2 m square pi square a square into e to the power lambda y. E to the power lambda y of course will be common to all the terms. So, we need not consider it because it will be cancelled. So, the characteristic equation will be lambda to the power 4 minus 2 m square pi square by a square plus m to the power 4 pi to the power 4 by a to the power 4 equal to 0. By solving this characteristic equation, we get 4 roots, because this is a fourth order equation, and from fourth order polynomial we get the 4 roots. You can see the roots are repeated, plus m pi by a plus m pi by a is repeated, and similarly minus m pi by a minus m pi by a will be repeated. So, according to the theory of linear differential equation, when the repeated root occurs, the solution can be written as y m equal to a m plus d m y cos hyperbolic m pi y by a plus b m y in plus c m sin hyperbolic m pi y by a. So, here you see I have taken the constant not in sequence, just arbitrary constant, you can take anything. But interestingly you can see, because of this cosine function, cos hyperbolic function and sin hyperbolic function, and when it is multiplied by a function y, then different characters of the function will be reflected. Now, let us see first, say if I multiply a m with cos hyperbolic m pi y by a, cos hyperbolic m pi y by a is a symmetric function. So, therefore, this term will be symmetric, but when I multiply d m y cos hyperbolic m pi y by a, you can note it that y is your odd function, whereas cos hyperbolic m pi y by a is a even function. So, product of odd and even function again will be your this odd function, even function. So, product of this antisymmetric term and symmetric term will be your antisymmetric, and symmetric will be your antisymmetric term. Again you come here, the second term b m y sin hyperbolic m pi y by a, here you can note that y is your this antisymmetric term, whereas sin hyperbolic is a symmetric term. So, product of antisymmetric and with another antisymmetric term will be symmetric term, and then C m sin hyperbolic m pi y by a is a antisymmetric term. So, I have grouped the symmetric and antisymmetric term here in this final solution after multiplying, after term by term multiplication. Now, here you can see the red color terms are all symmetric terms and blue color terms are antisymmetric terms. So, it can be easily verified that when the symmetric moment occurs or symmetric moment acts on at the two edges, opposite two edges, then the deflection function should not contain any antisymmetric term. So, therefore, we can drop this the blue color term, which is here the antisymmetric term. So, now in our problem we first consider the symmetrical moments are applied on the two opposite edges, that is m 1 is equal to f 1 x and m 2 is equal to f 2 x, but f 1 x is equal to f 2 x. So, we get the solution only with the red terms of the expression, that is the symmetric functions. So, dropping the odd terms are blue color terms here. So, accordingly I have written this solution as y m y equal to a m cos hyperbolic m pi y by a plus b m y sin hyperbolic m pi y by a. Now, note here that a m and b m are arbitrary constants of integration, and it can be only found by imposing the boundary conditions. Okay. Now, let us go to the boundary condition here. At the two opposite edges, the x is equal to 0 and x is equal to a, the plate was simply supported as seen here. So, the plate equation or deflected surface is written in this form, that along the x direction the sine function sin m pi x by a is taken, but along the y direction that function that y m y requires to be known completely once we can find the a m and b m. Okay. So, a m and b m are the arbitrary constants which are found by applying the S condition. So, in the plate you can see the x axis, this axis of symmetry is passing at the center of the plate, along the center of the plate in the x direction. So, it is symmetrical about x axis. So, at y is equal to b by 2 or at y is equal to minus b by 2, same moment exists. So, we take here y is equal to plus b by 2, w is 0 because this is simply supported. Now, since w is 0, the y m function will be 0. Now, y m is composed of symmetrical terms of the solution. So, I can write here instead of y I have written b by 2, and instead of y I have again here written b by 2 and sin hyperbolic m pi b by 2a. So, this is the equation that obtained by applying the boundary condition on deflection on the edges y is equal to plus b by 2. Okay. Minus b by 2 also you can obtain the similar equation. Okay. Now, from that equation it is readily seen that a m can be expressed in terms of b m. So, a m is expressed in terms of b m, and a m is now equal to minus b m b by 2 sin hyperbolic m pi by b by 2 a cos hyperbolic m pi b by 2 a. So, this ratio is tan hyperbolic. So, I have written this function as minus b m b by 2 sin tan hyperbolic m pi by b by 2 a. Now, note here that this quantity inside the parenthesis is written as a number alpha m, which is nothing but m pi b by 2 a, and it is a constant, depends on the harmonic numbers. So, m pi by 2 a is substituted as alpha m, and a m is written in this form, in the concise form, that minus b m a alpha m m pi divided by m pi tan hyperbolic alpha m, because from this substitution we can see b by 2 is nothing but a alpha m divided by m pi. Okay. So, this is the equation relating two constants of integration a m and b m. Now, we want to impose another boundary condition, so that the constants a m and b m are completely known. Okay. Now, let us see the second boundary condition. Okay. Second boundary condition have to be applied on the moment. So, moment that is acting along the edge are same, m 1 equal to m 2 here, because these symmetric functions are taken as a deflection series. It means that moment should be also symmetric. So, f 1 x is equal to f 2 x, we have taken f x, which is the distribution of the moment along the x, y is equal to plus minus b by 2. So, it is expressed as a Fourier series, m is equal to 1 to infinity, that summation goes up to infinity, and a coefficient of Fourier term, that is E m, a general coefficient is taken into sin m pi x by a, because any function you can express in terms of Fourier series. Okay. Now, let us see what is E m. Now, in that case, if I multiply this equation by sin m dash pi x by a, another equation, and integrate with respect to x from 0 to a, we get, because of integration with respect to dx, this integral will be sin square m pi x by a dx, and due to orthogonality condition of this sine function, you know that integration of sin square m pi x by a dx with a limit 0 to a will be a by 2. So, therefore, this right hand term becomes E m into a by 2, and the left hand function now it is a integral of f x multiplied by sin m pi x by a with respect to d x and in the limit 0 to a. Now, we can find the E m coefficient of the Fourier series, that is assumed for expressing the moment applied in the edges. So, E m is equal to 2 by a integration 0 to a f x sin m pi x by a dx. So, this equation represents the coefficient of Fourier series, which is used to represent the edge moment. Okay. Now, suppose the edge moment is a constant quantity, that is uniformly distributed moment, then in that case we assume that f x is m naught, where m naught is a constant value, is applied at y is equal to plus minus b by 2. That is, here at this edge your moment is also m naught, at this edge also moment is m naught. Okay. So, substituting this f x as m naught here, we require to integrate this function to find the coefficient of the Fourier series. Okay. So, after integration you can find that sin m pi x by a dx integration will be cos m pi x by a and with the limit 0 to a. So, when you put the limit and consider only odd terms, for even term the value of the integral will be 0. So, only for odd term we get the coefficient of Fourier series, which is used to express the edge moment, is nothing but 4 m naught divided by m pi, where m is the number that takes the odd integers only. So, the first term of the Fourier series will be 4 m naught by pi, second term of the Fourier series, coefficient of the Fourier series, second coefficient of the Fourier series will be 2 m naught by pi, and of course, that have to be multiplied by the sine function. That means, your the moment that can be expressed as 4 m naught by pi into sin m pi x by a plus 4 m naught by 2 pi sin 2 pi x by a plus 4 m naught by 3 pi into sin 3 pi x by a and so on. So, summation will go up to infinity, but you can note that for even integers the function value will be 0. For even integer the function value will be 0. So, therefore, E m will be only the 4 m naught m pi. Okay. Now, after substituting the value of E m, we can now express the distributed moment in a definite form, that is 4 m naught by m pi sin m pi x by a. This coefficient is very important, because when the uniformly distributed moment acts on the edges, then this coefficient represents the amplitude of the each of the sine terms, which is used to compose the series. Okay. Now, we apply the second boundary condition. So, second boundary condition when applied will give you the complete value of the a and b, the coefficient a m and b m. Second boundary condition, as you know, that it is simply supported along other two edges also. So, naturally the moment, the bending moment is 0 in the y direction. Now, bending moment in y direction is given by minus d del square w by del y square plus mu into del square w by del x square. That should be there, but because the edges are supported, so there will be no curvature along the x axis. So, therefore, the second term has no meaning here at the edges. So, edge moment is minus d del square w del y square equal to f x. F x means here this function. So, we have to substitute this f x here with this series. Now, let us see, we have substituted alpha m is equal to m pi by b 2 a and b by 2 is equal to a alpha m divided by m pi for some convenience in calculation or to write the expression in compact form. There is no other intention. So, hence equation 3 can be written as, equation 3 is on m, that is this equation, that you can write it the equation that we have found by this applying the condition of displacement on the boundary, then we can write this function as with a m equal to minus b m a alpha m divided by m pi tan hyperbolic m pi b by 2 a, and this is substituted as alpha m. Okay. So, after taking the second derivative of y m, because this function, the bending moment boundary condition requires second derivative of y m. So, when the second derivative of y m is taken and then substituting the boundary conditions, that is equal to f x, the edge moment is f x. So, d del square y by del y square equal to f x minus of course. Then using the relation between the constant a m and b m, constant a m and b m already found in equation 6. So, that we have utilized and we have written the series in the form of in terms of only one constant. Now, previously originally there was two constant, as you note here a m and b m, but we have seen that one constant is related to another constant by use of deflection condition. Okay. Then the another constant, the equation for determining the single constant b m can be found after applying the moment condition at the edges. So, applying the moment condition at the edges, we have got this series, complete series, say summation b m, and inside the bracket you will get the term which are coming from the second derivative of y m. Then it is multiplied by sin pi x, that is there, because sin m pi x by a will be always there when we take the even derivatives. With even derivatives, sin term will again appear. Then right hand term is f x, and f x is nothing but your this series 4 m naught d m pi sin m pi x by a. This is nothing but your E m, that is a constant of the Fourier series. Okay. Now, our intention is to find the value of b m, that is our intention. When you find the value of b m, then you can easily find the other constant a m. So, how it is found? You can see this is a series. So, when m is equal to 1, you will get b 1 into multiplied by something into sin pi x by a. When m is equal to 3, then you will get b 3, and this term substituted with m is equal to 3, and this is sin 3 pi x by a equal to right hand side with series of the term with m is equal to 3. So, like that you will get the infinite number of terms in the right hand side as well as infinite number of terms in the left hand side. Okay. So, in each term you will get the coefficient b m, that is b 1, b 3, b 5, b 7, like that odd number of coefficients will only appear, and because odd number of integers m is required for the solution. So, comparing the coefficients of the like term, that is the technique. So, after rearrangement I have written like that, because this you can see that cos m pi by b 2 a and cos m pi by b 2 a, this term is common. So, it is summed up and it is written in a compact form taking the common term together. So, it is written 2 m pi by a cos h cos hyperbolic alpha m plus alpha m pi by a sin hyperbolic alpha m minus alpha m pi by a tan hyperbolic alpha m cos hyperbolic alpha m, okay, into multiplied by sin m pi by x by a. Now, you can note that left hand side is also series of infinite number of terms, right hand side is also a series of infinite number of terms. Equating the coefficient of like term, that is here you are getting b 1 coefficient of b 1, and here you are getting another coefficient with when m is equal to 1. So, that can be compared or equated, because the series has to be equal when the coefficient of like terms are equal, otherwise it cannot be equal. So, it is a sine series. So, in the both sides you are getting sine series. So, each term of the sine series will be equal, then only the series is equal. So, from that condition, for any general term m, we get B m equal to 4 m naught d m pi into this. So, this can be easily verified from this expression, that coefficient of sin m pi x, that is the mth term, will be 4 m naught d m pi, and this is the coefficient of B m. So, B m will be this divided by this term that you are getting. Okay. So, B m equal to 4 m naught divided by d m pi into this factor. This factor is coming as a reciprocal of this expression. So, 1 by this 2 m pi a cos hyperbolic alpha m plus alpha m m pi by a sin hyperbolic alpha m minus alpha m pi by a tan hyperbolic alpha m cos hyperbolic alpha m. So, very carefully we have to see the expression, otherwise even if you miss one term, it will give you wrong results. So, carefully you have to see the all terms are included in the expression. Okay. So, now A m is found out earlier, B m is known. So, A m can be easily known, because A m is expressed in terms of B m. Okay. So, now the solution can be written in terms of B m, because only one constant is required, because A m is now expressed in terms of B m. Okay. So, we get this function as the solution of the homogeneous differential equation for this plate equation, homogeneous differential equation that resulted after substitution of the Levy's series in the partial differential equation. That is actually the separation of variable technique that we adopted, and we ultimately get this function y m equal to this B m multiplied by y sin hyperbolic m pi y by a minus a alpha m pi tan hyperbolic alpha m cos hyperbolic m pi y by a. So, this is the series, all right. B m is known from that expression completely. So, now y m is completely known, that means deflection is completely known. So, deflection can be written as now, because we know that this B m that we have found earlier contains 4 m naught by d m pi. So, d pi is the constant term, m naught is also constant term. So, it is taken outside the summation term, and inside the summation term all the quantities which are dependent on the wave number, or you can tell the half wave number m is written, because the sum have to be carried out with the respect to the half wave number. So, therefore, this term I have separately written as B dash m equal to this. So, deflection series is completely known now for the edge moment, which are symmetrically distributed on the two opposite edges. That means, two opposite edges has equal magnitude of moment if the moment is uniformly distributed, or an equal nature. That means, it is trying to sag the plate in this case. Sometimes it may try to hog the plate also in the both the cases, then also the symmetrical distribution of moment has to be considered. Okay. So, after getting the symmetrical distribution of function, we can get completely the deflected surface, from which we can now find the deflection at any point on the plates. Of course, in this case for symmetrically distributed load, we will get this maximum deflection at the center of the plate. So, maximum deflection is found at x is equal to a by 2 and y is equal to 0. So, this is the center of the plate. So, after substituting this value in the this term, when m naught is specified, we can completely find out the deflection in numerical after putting the numerical value of this material properties, because D contains the material properties. What is the parameter involved in D? Parameters that is involved in D, capital D is modulus of Young's modulus of elasticity and Poisson ratio of the plate. So, these two values are important to calculate the deflection of the plate, as well as the dimension of the plate A and B should be known. Thickness of the plate is also important to find the flexural rigidity of the plate. So, once you get the deflection of the plate, then you can find the shear force if it is required Qx and Qy. You can find the Kirchhoff's H shear, that is a shear that is found after combining the vertical shear force with the shear force contributed by the twisting moment. So, these two force effects are combined to give a S shear, which is due to Kirchhoff, and therefore, it is known as Kirchhoff S shear. So, all these distribution you can find out. In addition, you can find the corner reaction force that is developed at the corners due to twisting moment effect on the two adjacent edges. So, this corner force actually will be trying to leave the plate. If the plate is not properly anchored or held down, then it will try to leave the plate, and therefore, in case of simply supported plate, generally the corners are provided with a anchoring device. In case of this RCC slab, which is modeled as a plate, is reinforcement of special nature is provided at the corner in the form of mesh, top and bottom, to prevent the or to reduce the detrimental effect of the corner lifting force. Okay. Now, we go for antisymmetrical moment at the edges. Now, here we see that F 1 is equal to minus F 2 x. So, this is the antisymmetric case, but magnitude is same in both the cases, but they are of opposite nature. So, F 1 x is equal to minus F 2 x, and m y at y b by 2, whatever distribution is there, you will get opposite distribution or opposite nature in the other edge. So, at y is equal to minus b by 2, it is minus m y, and at y is equal to b by 2, it is m y. So, in this case, we shall take odd terms in the homogeneous solution of the differential equation. So, differential equation that you know earlier that I have shown you, it is obtained after substituting the Levy series in the partial differential equation of the plate, and then separating the variables y, we get this differential equation. So, this differential equation is a fourth order ordinary differential equation, and this can be solved for homogeneous function, or homogeneous solution can be obtained by using the characteristic roots of this equation, and it is shown that this solution contains the odd terms as well as even terms, that is found in terms of cos hyperbolic and sin hyperbolic terms. Originally, the function was written in the form of exponential term, but exponential term is converted into hyperbolic terms. So, that we can easily understand the influence of this symmetrical and antisymmetrical term in the plate, and importance of this term for case of symmetrical loading and antisymmetrical loading is now giving advantage for the solution of the plate problem. Okay. You can note here that this is the symmetric term cos hyperbolic, y sin hyperbolic is again symmetric term, because y is antisymmetric, sin hyperbolic is antisymmetric. So, product of two antisymmetric term is your symmetric term. Then sin hyperbolic term is again your this antisymmetric term, and d m y cos hyperbolic m pi y by a is again your antisymmetric term. Now, since the moments are antisymmetric, so we need to drop this term b m and a m coefficient, we need to drop. Okay. So, from physical reasoning that the deflection of the plate should contain the antisymmetric term, that means the plate will deflect in antisymmetric manner. Therefore, in accordance with that, we have to take only the antisymmetric term, that is sin hyperbolic m pi y by a d m y plus d m y cos hyperbolic m pi y by a. So, that means we can retain only the two constants in the solution C m and d m, which are needed to be found out. Okay. So, dropping the even terms, Now, we write the solution as y m y equal to C m sin hyperbolic m pi y by a plus d m y cos hyperbolic m pi y by a. You can see both the terms are antisymmetric terms. Now, let us also express the moment, antisymmetric moment in the form of Fourier series. So, here I am taking as a different constant e dash prime, e prime m. Previously, we have taken e m, now we are taking e prime m sin m pi x by a equal to m prime naught. Okay. So, this is the Fourier series, and because this is actually in one edge it is plus, in another edge it is minus. So, after multiplying this function with sin m dash pi x by a and integrating in the limit 0 to a, we get again this you will get this function 4 m prime naught divided by m pi. So, this parameter will appear for the constant e prime m. So, the coefficient of Fourier series is now known. So, first term will be 4 m prime naught equal to divided by pi. Second term, that is the second term is a odd term. So, it will be 4 m prime naught divided by 3 pi, like that it will go. Only odd terms need to be taken, because even term after integration vanishes, because after integration the cos function will appear, and when you put the limit 0 to a, you will find that it will be 0 for even number of terms. Even number of terms, it will be 1 minus 1, that cos whatever even function cos 0 is 1 and cos 2 pi is also 1. So, 1 minus 1 will be 0. So, therefore, even terms will not contribute to the Fourier series. So, only odd terms will contribute to the Fourier series, as it was shown in case of the symmetrical loading also. So, therefore, distributed moment f x can be expressed as a series 4 m prime o divided by m pi into sin m pi x by a. Now, one thing you observe, that this quantity m prime naught is a known quantity, and in case of distributed moment, that is which is uniformly distributed, we will get the constant m naught in the two edges, but it will be opposite in other edges, that is in nature. If in one case it is sagging, in other case it will be trying to hog the plate. Okay. So, observing similarity in procedure to be followed in two cases. Now, we have observed one thing, that procedure of finding the solution in symmetric case and antisymmetric case is similar. There is no drastic change in procedure, because the same steps are followed, that is you express the moment in terms of Fourier series, and then Fourier series coefficient is found by using orthogonality condition of the sine function. Then you can see that this boundary condition need to be applied. In the earlier cases, the condition was this deflect, because it was also simply supported, and now also it is simply supported. So, at the edges y is equal to plus minus b by 2, you will get the condition as deflection 0 and bending moment 0. But since it is an antisymmetric problem, so all the terms in the deflection surface should involve the symmetric terms. So, there is no contribution will be antisymmetric terms in the deflected surface. So, observing this fact, we can now replace the several terms by their symmetric term by their antisymmetric term, antisymmetric counterpart in the deflection series. So, deflection series is w x y, and w x y you can see that it is nothing but w x y is your Levy series. In the first I have shown, this is the w x y, and y m contains the symmetric and antisymmetric terms. In the present case, we are dealing with antisymmetric cases. So, in that case our only antisymmetric terms are of importance. So, keeping the antisymmetric terms, that means using the earlier results, we can write the deflection, that is y m, simply by replacing that sin hyperbolic by cos hyperbolic or cos hyperbolic by sin hyperbolic, tan hyperbolic by cot hyperbolic or cot hyperbolic by tan hyperbolic in the equation obtained in case of symmetrical cases, because we have these terms only in the symmetric cases, there is hyperbolic functions in the expression of y. So, replacing this term by appropriate antisymmetric term, antisymmetric counterparts, we can now write y m y equal to d m y cos hyperbolic m pi y by a minus b by 2 cot hyperbolic alpha m sin hyperbolic m pi y by a. In the earlier case, this term was your sin term, sin hyperbolic term. So, that the product of two antisymmetric term was symmetric, but now since this is antisymmetric problem, with sin hyperbolic is replaced by cos hyperbolic, and therefore, product of one antisymmetric term and one symmetric term is antisymmetric. So, this is reflecting the true nature of the problem. Then here tan h alpha m was replaced by cot h alpha m, and this term was your this cos hyperbolic in the earlier case, which was the symmetric term. Now, it is replaced by sin hyperbolic function. So, all the symmetric terms are now replaced by antisymmetric terms, where d m in the similar fashion we now express the coefficient d m. We know that this function for this is found after applying the second boundary condition, that is due to bending moment at the edges. So, when we apply the second boundary condition, second derivative is of importance. So, equating second derivative to the given moment function, we can now get the series in the left hand side and the right hand side. So, left hand side also contains infinite number of terms, right hand side also contains infinite number of terms. So, now equating the coefficient of like terms, we can find the coefficients of each of the term in the series. For any general term m, we found the coefficient d m equal to 4 m dash o divided by d m pi, and is a multiplied by a factor this 2 m pi a sin hyperbolic alpha m m pi by a cos hyperbolic alpha m minus alpha m pi by a cot hyperbolic alpha m sin hyperbolic alpha m. One thing is observed here, that in earlier cases all the terms were just this counterpart, that is now only the symmetric terms are used. Earlier all terms were symmetric terms, now the antisymmetric terms are only used in the expression. So, we now write the w x y, the deflection series, as this, where d dash m is found with this, d dash m is this term that is found here. So, now two conditions are analyzed, one is antisymmetrical condition, symmetrical condition first, and then second is antisymmetrical condition. Okay. So, you have understood the procedure. Now, if there is any general type of distribution, so general type of distribution I mean that in one case it may be symmetric, in another case it may be antisymmetric, or in both cases there may be similar nature of moment, but magnitudes are different. So, it is known that any arbitrary function can be decomposed into symmetrical and antisymmetrical component. That is well known fact in mathematical physics, or you can say that in mathematics. So, any arbitrary function is decomposed into symmetrical and antisymmetrical terms. That means, here this function in the one case it is m 1 x, in the other edge it is f 2 x. So, we write the components m 1 prime will be half of f 1 x plus f 2 x as a function say g x. So, now we find the deflection of the symmetrical distribution of function with this component. So, if these two components, if this component of moments are acting on the two opposite edges, this is taken as a symmetrical part. Okay, this is taken as a symmetrical part. We can use this symmetrical the expression for the deflection that we have derived earlier. Now, in the second case, the antisymmetrical term will be half of this f 1 x minus f 2 x. So, that has to be used now with the antisymmetrical term in the deflection that we have just analyzed this for antisymmetrical moment. So, two conditions are obtained separately, one is antisymmetrical symmetrical moment condition and another is antisymmetrical moment condition. But given the moment distribution in the two opposite edges, any moment distribution, we first decompose into two functions. One is symmetrical function, that is if the edge moment in one edge is f 1 and the edge moment in another edge is f 2, then symmetrical distribution of function will be f 1 plus f 2 divided by 2. Antisymmetrical distribution of function that will take in the second case will be f 1 minus f 2 divided by 2. So, two cases are analyzed separately with the help of our known results, and then we superimpose the two results of deflection to get the deflection for any arbitrary moment. For example, this edge of the plate is subjected to a moment that is shown here is the moment that is acting in the clockwise direction here, say 10 kilonewton meter per meter, and in that case it is also acting in the clockwise manner, but the nature of the moment is such that it will produce the antisymmetric deflection. So, therefore, these are any general case. Okay. So, if this is a 10 kilonewton meter per meter, and here for example, this is another moment of nature symmetrical. So, it is say 5 kilonewton per meter. So, in that case, in the first case we have to obtain the deflection of the plate using the symmetrical moment in the two edges as 10 plus 5 divided by 2, that is 7.5 kilonewton meter per meter. So, in the second step we will find the deflection of the plate for antisymmetrical moment, which is imposed by subtracting the result 10 minus 5 divided by 2 by using the moment value as 10 minus 5 divided by 2, that is your 2.5. So, in one case the result will be obtained by the using the edge moment as 2.5, in another case the result will be obtained with the edge moment 7.5. Now, if you add these two results, you will get the actual distribution that you are requiring here. So, in this way, by method of superimposition, we can obtain the deflection of the plate for any general distribution of moments. Okay. Now, let us see the application of these results for further analysis of the plate. Now, here we are dealing with the closed form expression of the deflection, that is the exact solution of the differential equation is obtained in Levy's method as well as in Navier's method. Of course, here I am discussing the Levy's method. So, we will use the Levy's method for edge moments to other support condition. So, Levy's method is used for getting the results of the deflection of the plate subjected to edge moment, symmetric as well as antisymmetric, and that condition we will now use to a plate which has other support condition not directly following the Levy's condition. Okay. So, let us see how it can be done. It is easily conceived that the edge moment results of the deflection of the plate whose two opposite edges are simply supported can be used to rectangular plate with other edge conditions by the method of superimposition. That you know, say from your elementary structural analysis, you know that a fixed beam can be analyzed by first using a simply supported beam and then using a beam with a n moment and then superimposing the result such that the moment at the end that is applied will make the slope at the end to be 0. So, that gives the fixed end condition of the beam. So, this principle will be applied here in case of plate also. So, we will illustrate the procedure to be followed in two cases: a rectangular plate with two opposite edges simply supported and other two opposite edges fixed. Then second case, a rectangular plate whose all the edges are fixed, that is a clamp plate. Okay. Let us see, in the first case we have to deal with this condition that of course already obtained in my earlier classes, that two edges are simply supported, x is equal to 0 and x is equal to a are simply supported if this length is a and this is b, and this is clamped, y is equal to 0 and y is equal to b is clamped. But of course, here we are taking the x axis running through the middle of the plate. So, naturally the boundary condition will specify at y is equal to plus b by 2 and y is equal to minus b by 2. So, at y is equal to plus b by 2 or y is equal to minus b by 2, we have the fixed boundary condition. Okay. That condition we have already obtained, solution already obtained using imposing the boundary condition at the two opposite edges with the help of the Levy series. Okay. But now, we shall try how we can obtain the similar result with the help of the results obtained in today's class. Today's class we are focusing on the deflection of the plate subjected to edge moment. So, now this condition can be written as an equivalent of the simply supported plate subjected to UDL. Of course, we are analyzing the plate for UDL. So, simply supported plate subjected to UDL plus simply supported plate subjected to a edge moment which is symmetrical. So, if we superimpose these two conditions, this will reflect this condition provided the M has to be found in such a way that it will make the slope along the y direction as 0. So, that condition must be satisfied by the particular value of M. So, let us see how we can proceed. This problem can be solved by Levy's single series, that is obvious, by imposing clamp boundary condition that we have already obtained it, but now in this method we are discussing the use of the results obtained for edge moment. So, in figure 1, the plate is simply supported along the all edges carrying the UDL whose results are already known by us, and this is the plate in which the two opposite edges are simply supported, but two opposite edges are subjected to this same moment, that is symmetrical type of moment. Okay. So, for this condition 1, the deflected series is known. From our earlier analysis, I have written this result directly, you will get in my earlier note this result is given. So, this I call it as W1 because this is the deflection due to UDL. Okay. So, once the deflection is obtained, that means Ym1 is already known due to this UDL, and we write the deflection series as it is, because two opposite edges x is equal to 0, x is equal to a are simply supported. Okay. So, for second condition, that is the edge moment applied condition, we call the deflected series as W2. So, W2 is now obtained as y2y sin m pi x by a, and Wxy that just now we have obtained in terms of m naught, and the coefficient b dash m etcetera all are mentioned in the earlier slides. So, this W2 is written as this. Superimposing these two conditions provided we will resolve the actual deflection of the plate subjected to uniformly distributed load with the edge condition that two opposite edges are simply supported and two opposite edges are fixed. Only will be true if the value of m is such that it will make the slope as 0. For that condition, we will impose this del w the slope along the y direction for w 1 plus slope along the y direction for w 2 at y is equal to b by 2 equal to 0. The above equation is applied in accordance with the principle of superposition. We obtain the value of m naught. Once you know the value of m naught, the fixed end moment at these edges along these edges are known as the series f x is equal to 4 m naught m pi sin m pi x by a. After summation with infinite number of terms, it will represent the uniformly distributed moment. Okay. So, deflection of the plate is then w x y equal to w 1 plus w 2, all are functions of x y. Okay. Now, let us see the second case. That is the most important condition in practical purpose. The all edges are fixed in most of the cases for better rigidity and for better stability of the structure. So, here you can see that because of the clamp condition along two edges, the neither Navier condition nor Levy's condition will yield the closed form extension. So, this is decomposed into three parts that we need to superimpose. One is plate with all the edges are simply supported, that is given as case 1, with q naught is the load, uniformly distributed load. Then the moment applied along the edges parallel to x axis, that is y is equal to b by 2. Here of course, you can note the difference is there because the plate is symmetrical with respect to x and y axis. So, we have taken the origin at the center of the plate. So, with respect to origin at the center of the plate, that y is equal to b by 2 and y is equal to minus b by 2, the condition that m 1 is applied here. Thirdly, this simply supported boundary condition, but x is equal to minus a by 2 and x is equal to plus a by 2, the moments are applied if the a is the length of the plate. So, you can see the three condition when superimposed will reflect the actual condition, provided the m 1 and m 2 should be evaluated in such a manner that it will make the deflection slope at the edges along the y direction and along the x direction as appropriate may be should be 0. In the appropriate cases it should be 0. So, accordingly we divide the case into three types. We have divided the problem into three cases: a simply supported plate subjected to UDL, case 2 a simply supported plate subject to symmetric moment along y is equal to plus b by 2 or minus b by 2, case 3 a simply supported plate subject to symmetric moment along x is equal to a by 2 and x is equal to a minus a by 2. For first two cases deflection functions are given, because these two cases requires that the plate is symmetrical about the x axis. Okay. So, that we have got, but in the origin is taken of course in the center of the plate, and therefore, the x has to be replaced here by x plus a. So, that should be noted very carefully, that x has to be replaced by x plus a. In the second case, that is the third case, in this case it is a third condition, that is the moments are applied along the edges x is equal to 0 and x is equal to a. For that, the Levy's series can be written as capital X is a function of x into sin n pi y by e. The Levy's series is now interchanged, that is the sine function previously it was the summation with m, that is half wave number along the x direction. Now, with respect to n, that is half wave number along the y direction. Here origin of the plate is again at the center. So, y have to be replaced, but by y plus b in the expression. Okay. So, after superimposition of these three results, three cases, we will get the w as w 1, w 2, w 3. Now, the condition for fixity along all edges have to be satisfied only when at y is equal to plus minus b by 2, the slope is 0, that is del w 1 by del y plus del w 2 del y plus del w 3 del y equal to 0 in all the in y direction. Similarly, the slope in x direction should be 0 that means at the edges. So, x is equal to plus minus a by 2 del 1 del w 1 by del x plus del w 2 by del x plus del w 3 by del x equal to 0. So, we are getting two equations, and these two equations will yield linear equation which involves the coefficient of the moment series. Okay. The moment is expressed as E1, E2 etcetera in the Fourier series form. So, we will get the coefficients E1, E2 etcetera, and the general term of the coefficient Em or En in the two cases, because the moments are applied in one case along the x axis, and in another case the moment is applied along the y axis. So, you will get the two coefficients of this moment function, and therefore, the fixed end moments are determined. Once the fixed end moments are determined, then you will be able to find the deflection completely. So, you have noted here that with the condition of edge moment, the results known for the edge moment cases in a simply supported plate, and with the results known for the simply supported plate with UDL, we can now analyze the plate whose all edges are clamped and your this subjected to UDL. So, the procedure can be applied to other types of load also. Okay. So, let us see what is the summary of this lecture that I have delivered today. In this lecture, we outlined the approach for finding the solution of the deflections of a rectangular plate, of course, simply supported along all edges and carrying moments at the edges. So, edge moment condition we have analyzed in today's class. Two cases are discussed. One is opposite edges subject to symmetric distribution of moment, in which case we use the even functions in the homogeneous solution of the plate equation. In the second case, opposite edges subjected to antisymmetric distribution of moment, in which case we use the odd functions in the homogeneous solution of the plate equation. Then we discussed the steps for the solution of any arbitrary distributed moments, making use of superimposition principle. Lastly, steps were discussed to utilize the deflection results derived for the simply supported rectangular plate subjected to uniformly distributed load and edge moments to obtain the solution for the cases when the rectangular plate has two opposite edges as simply supported, but other two opposite edges are clamped and all edges are clamped. So, these conditions are analyzed, that means, we actually obtain the exact solution using the Levy's condition for superimposing different results. This concludes the mode generality. This concludes that mode generality in application of Levy's method compared to Levy's method compared to Navier's method. So, Navier's method is only restricted to plate which has all edges simply supported, but in Levy's condition, Levy's method, you will find that this condition can be relaxed by using the superimposition principle. Even we have gone for a plate which has all the edges clamped, but originally the Levy's equation is applied, Levy's series is applicable when two edges, opposite edges are simply supported and other two edges may be of any boundary conditions. But using different results for different loading conditions, loading and edge moments, we have now arrived the results of clamp plate, that is all edges are clamped using the Levy's method, which is actually the exact solution of the differential equation. Okay. So, thank you. Next class we will see the other problems in the plate. Okay. Thank you very much.